right, welcome back everyone. So, new week that we get to start exploring processes. So, all right, come on, settle down, settle down. Volume. Okay, so where did we leave off last time? So last time we looked how to transform a process and actually run another process, but we didn't actually get to the point where we actually create a process. So finally we get to do that today, and hopefully I have a better chat set up, so I'll actually read it now. So now I have time, so that should work better. So we had that initial question before of like, why the hell am I doing this thing of replacing a process? And that's the only way to run a new program. Why don't I just create a new process from scratch and tell it what program I want to run? So if you did that, you would load that program into memory, create the process control block just from scratch out of thin air, instead of just copying instead of doing what we'll see today. So this is what Windows does. So Windows actually has a create process system call like thing. And what it will do is it will just create a new process for you out of scratch, and you tell it what program you want to have run. But Unix is a bit more flexible in that it decomposes this process into two steps. So the process creation, which is separate than running a new program. And we'll see that that's actually a useful thing to do, and it actually gives us some more functionality. So what Linux does instead, or any Unix, is instead of creating a new process from scratch, it just clones the currently running process. So what it does is pause the current running process, copy its process control block into a new one, so it makes a complete copy of that running process, reuses all of that information, so any libraries it has open, any files it has open, all of its contents of memory, everything like that, they're all copied. And then the only difference between these two processes after the system call, which is like a clone, is the return value of that system call. And Unixes maintain this like strict parent-child relationship. So whatever process initiated the call is called the parent, and the other one is called the child, so because it created it. So, and that's the only difference, and there's a strict parent-child relationship, and every single process on Unix follows this. So every single process will have a parent. And then the nice thing about this is if we don't want to continue running a new process that's the exact copy of whatever was running, minus, its return value, well, if you want, you can optionally have it create a new process by doing that exec-ve system call and then replacing the current running PCB and starting a new process. So it's a two-step process to create and run a different program. So this is kind of what a typical process tree looks like of that parent-child relationship. So everything at the top is a parent, and whatever is below it with that line is its direct child. So if you have a virtual machine or you use a Unix system and you do top or htop, something like that, this will be your parent-child relationship. And there is only one special process, and that is process with process ID 1, usually just called init. And the kernel's only job when it's finished booting the hardware, all it will do is create a new process with process ID 1. So each process gets assigned a number, which is just the way to identify it. It will be a unique number. So when the kernel is done booting, it will create one process with process ID 1, and it will load typically whatever is in like sbin init or something like that. So a program called init. And that process is responsible for creating every single other process on your machine. So in this case, we can see that, okay, if we want to follow the tree to, say, Firefox or something like that, well, init create a process called systemd user, which is a weird thing. Basically, that's just another manager of processes for your specific user. And then you might have like a desktop environment, like the actual your actual desktop, and it would be something like GNOME Shell or something like that if you're using one flavor of Linux. And then through that, wherever that would be running as a process, and then you would go like pick applications Firefox and launch it, and that would launch Firefox as part of what it does when you click that Firefox icon, and that would be running as a process. And then Firefox might have a bunch of different other processes also called Firefox, which, funnily enough, there's going to be one new process for each tab on Firefox because that's basically how they architected Firefox. So each of these processes would be a different tab, for example. And then another way you could go is, hey, if I opened a terminal, then it might have a process like the terminal server, and then within that, I have my shell, which would be ZSH or bash or something like that. And then next would be whatever command I started executing. So if I'm running something like htop, that would be the thing running. So that would look something like this if I go in here. Oops. And you probably can't see that at all. And I should probably get out of there. So if you do something like this, oops. So if you do something like this will show you all the processes running on your machine and try and draw like a tree on that command thing. So here we can see process ID 1 all the way on the left there. Hopefully everyone can see it. And then see whatever processes it creates. And you can go ahead and explore every single process on your machine. So these are all the processes that are actually running. And for lab 1, you are writing a simple version of this program. So you're going to explore, you're going to see all the programs running on the machine and print out their names as part of lab 1. So this gives you a bunch of information all for lab 1. You're going to print off as like this process ID there, and you're going to write out not what command got run that the process represents, but what its name is. So if you run htop, that would be in your dev container if you set up lab 1 already. If not, oh yeah, if you haven't logged on to the GitHub site for the lab, please do that because I have to like manually approve you and create your repository. If you leave it to the last minute and I'm asleep, you are definitely screwed. So please just do it as soon as possible. All you have to do is log in. It shouldn't take more than like 2 seconds, or you could do it now. And then, yeah, so that's about lab 1. So if you wanted to explore knowing a bit more about this parent-child relationship, you could explore, see what process created which, and next we'll get into how to create those processes. But first, note that as opposed to before, Linux terminology is a bit different. I just showed you very generic terminology. Linux terminology is a bit different. So there's this proc file system, which is what you'll be playing with in lab 1. So there's like /proc, and then there's a bunch of folders and files in there that you can explore. Every entry in proc that has a number represents a process ID, and you can actually poke around and see all the information about the process you want. So if you wanted to look up the process state, like that state diagram before, there's a file in there called status, and one of the lines in it just says state. That will say what the state of that process is. So you could check any state of a process just by reading that file and looking for the line state. And in there will be one of those 5 states, running or runnable. So Linux doesn't make any difference between running and waiting or ready. It just says both are running. And then there are 2 types of sleep or blocking. There's interruptible sleep, which means you could wake it back up and it might be able to do some useful work. And then there's uninterruptible sleep, which means no matter what, it won't wake up. It's waiting for a network connection or something like that. So even if you woke it up, it couldn't make any progress. So it just kind of stays around. And then optionally, you have some things where you can manually stop and start a process that typically aren't used that much, but you can do it, and that's that stop state. And then the last state is this weird term, zombie. So we will learn what zombies are in the next lecture, and it will get a little bit weird, the terminology, or kind of gruesome, but it's always kind of fun. So that's basically how you translate it for Linux, and you can poke around that proc file system and you will get more familiar with it in Lab 1. So, like I said before, just so you have it on Unix, all the kernel does whenever it boots up and initializes itself and it's ready to run programs is all it does is run a single process. So it will just run typically init, which would look for in sbin init typically on your file system. And that is responsible for executing every single other process on the machine. If that process does not exist, then the kernel thinks you're shutting down and it will exit for you and shut down your computer. So basically, if that process exists, your operating system exists. If that process is gone, that means you want to shut down the computer, so the kernel would go ahead and shut down the computer for you. So for Linux, there's a bunch of different things that could implement init. You could even do your own init if you really wanted to. But for Linux, it's typically something called systemd, but there's a bunch of other options that are subject for debate. And on some other operating systems, there might be other like weird tasks to kind of do some bookkeeping things. So some operating systems like Windows would make a fake idle process, basically to keep track of how much idle time your CPU is just sitting around for. And then finally, these magic numbers. So again, these magic numbers for file descriptors are just convention, and they're something you should probably remember if you're monkeying around with any Unix process at all, because you have to manage these if you're creating processes and make sure that they actually are what they're supposed to be. So every standard convention is that when you start a process, there are at least 3 file descriptors open, 0, 1, and 2. File descriptor 0 is standard input, file descriptor 1 is standard output, and file descriptor 2 is standard error. So if these are only your file descriptors where you read and write bytes from, well, we kind of have some knowledge as to what our terminal emulator actually does, because these just deal with raw bytes and it doesn't really matter past that. So whenever you type into something like a terminal, well, some of the jobs it has to do is actually translate your key presses into bytes and then writes them to standard in so your process can go ahead and read them. And then everything that you write to standard out or standard error, well, it has to be on the other side of that to read those bytes out, which would be typically ASCII characters. And then it actually has to draw those bytes out for you on your display so you can actually see them. And then part of the other fun that we'll get into with them is you can mess with the file descriptors and redirect them to other things if you just don't want to display them, if you want to send them somewhere else. The power of Unix is you can go ahead and do that. So if you really want to see, like if you're debugging, maybe you have a bunch of open file descriptors or maybe something went wrong. So in that proc directory, there's also this fd directory, and that tells you all of the open file descriptors for a process. So if you use a ps command, that will show a list of processes matching your user. There's lots of other flags. And in fact, if you don't like them, well, you're writing basically ps for lab 1. So you could add additional features to that if you want to see anything else about a process. But for example, if I run a terminal emulator and see what the file descriptors are, I can read what standard in, out, and error are, and they'd be something like dev.tty, which is like a terminal device that you don't have to know. And let's go ahead and see, just for proof of concept, what is actually running on my terminal. So I just happen to know, because I went through the lecture, that my shell is running as that process ID. So if I go there and look at the fd directory, I can see what the file descriptors are. So there's a few other open ones, but you can see here that they're a little bit different. 0, 1, and 2 are actually all the same thing, and they're this dev pts thing, which looks a bit weird. That's a pseudo terminal, which you don't have to know the details of it, but it's just a fake device that I can read and write bytes to, and that's basically what your terminal emulator does. But you can see it has a few more open things, and you can explore this all you want to like kind of get the nitty-gritty details of what's going on. you can also use this command. Because you can do that, if you see, has anyone ever seen that error message before? Like, oh, some random process has this file open and you have no idea what that is? Well, on Unix, because you have this, you can figure out what it is. So for example, you can use this ls command, or ls of, which will tell you what processes have a file open if you really want to know. So one thing I could do is I could see what processes actually have libc open, which basically is probably every single process on your machine. But if you want to, you could do something like that, and it will show you everything that has libc open and is using the C standard library. So that's kind of a cool thing you can do. You don't really need to know how to do that, but it's kind of the power of this model and having everything nice and visible for you. Oops, wrong button. Okay, so that's a little demo of that. You can do that for any file on your machine you want. So this is actually the meat and potatoes of today. So you can find documentation using man whenever you do these labs. Like if you do man exec VE, you can get some documentation for it. Today will be that cloning process. It's called fork. So it's called forking. And then we'll see a wait system call in the next lecture. But you can always use like man function name to look up documentation. And sometimes if it isn't what you expect, you might have to give it a number. So for example, if you do man fork without any number, I believe it gives you like documentation for awk or something that you've probably never used or never heard of. So if you want the actual like system call wrapper, you have to do man to fork or something like that. So that's just something to pay attention to. But so let's talk about fork. So its API is quite simple. It creates a new process, which is a copy of the current running one. And the reason I introduced this so early is this might actually hurt your brain a little bit because now processes don't start at main and keep on executing. Now you can create a new process in the middle of another running process. So we'll have to probably get used to it and practice it again. And it has a following API. It's nice and simple, where it doesn't take any parameters whatsoever, and it returns just the process ID of the newly created process. So it's like a C standard wrapper. So if it returns -1, that means an error happened and you didn't create a new process. But typically, you always assume it returns successfully. Otherwise, your computer's probably dying in some respect, and you probably have much bigger problems. But typically, we won't see failures. We'll see 0 returned if it's the child process, and we'll see a return value greater than 0 in the parent process, where that return value is the process ID of the child. So the child will get a new process ID as part of being created, and then the parent will get that process ID as a return value, and the child will just get 0. And that's the only way to distinguish what the original process was and what the new process is just the return value of fork. Otherwise, they are exactly the same. And we'll see over and over again what I mean by exactly the same. So now there's 2 processes running, and the operating and they like literally exact copies. So they can access the same variables, but they're completely separate and independent copies of each other. So if you modify X in one process, it won't touch the other process. They're completely separated from each other. So we'll see mechanisms behind this, because this seems like really slow, because I mean it's an exact copy. So like even all of the contents of memory will be the exact same, which might seem really, really, really slow. Like, hey, if it's Firefox and it's like 10 gigs or something like that, because browsers, use that much RAM. Well, I don't want to have to copy 10 gigs just to create a new process. That would probably be really slow. We'll see techniques to actually speed it up, but for the purposes of you using it, it's like an exact copy of all the memory contents as well. So here is our example. So fork example, we'll have one process in each branch. So luckily, we start reading programs from main as usual. So if we execute this program, it would start executing at main. And then the first thing it does is call fork. So fork would create a new process. And now, right before this return value, we would have two processes. And now in the parent, it would get the process ID of whatever was just created, say created process ID 101. And then in the child, which would be process ID 101, it would get 0 return there. And now there are two processes that can execute. It's up to your kernel whether which one to execute, or if it wants to run them both in parallel. That's up to the kernel. You don't get to decide. It's up to the kernel. And then at this point, well, I'll assume that there's no error so that this branch wouldn't be taken. So now there are two processes. One, the child process, would be an exact copy. So at the time of the fork, when it's an exact copy, there's nothing defined or anything. So there's not really much to copy. And then it would return 0 from fork. So there'd be two processes. When I execute this, the child process would come into this branch and then print off all this information about the child. So it would print off whatever fork returned, and then it would print its process ID, which is done through another system called get PID. So that will return your process ID. And then you can also check the child's parent ID independently through another system call. So that's get PID, so get P parent process ID. And then in the child, it would be done this if statement and then fall through to the end of it and then return 0, which would call exit and then end that process. Okay, 1 second. And then in the other case where the parent, there'd be another process that would check if the process ID is 0. It's not. It would be the process ID of the child. Then it would come in this, print off parent return whatever it was. In this case, I said 101. Then print off its process ID and then its parent. And yeah.
So just to confirm, in the last two, like once it gets past the error, if there's no error,
Yep.
those, the if and the else run simultaneously?
Yeah. So
Two processes?
yeah. So the question is, assuming fork doesn't have an error and I get past that, then both branches run simultaneously. And the answer is there's two processes, and they may or may not run simultaneously, and you may or may not know what order they run in. In fact, you definitely won't know what order they're in.
So it could be random. Does it change each time? Like, for example, could it print the parent stuff before the child stuff?
Yeah, so it could be random depending on whatever execution, and this is the stuff you'll get used to in the course where you have no control and you don't know which one is running first, and it is completely up to the kernel to decide. Yep.
The child process will start executing at line 3, right? Like this won't create an infinite loop of copies.
No, so after the fork, right after the fork returns, that's the new process.
Okay.
So there's a new process. You can think of it right after the fork, and it would get a different return value. And then otherwise, the two processes are exactly the same. Yep.
So if the two processes are the same, then do the if and else return like the same print statements?
So,
Are the printfs, do they return the same?
so the two processes are exactly the same, except for the return value of fork.
So get PID and get PPID will be the same?
No, so they'll be different. So let's go ahead and run this. So this is the start of, like, unfortunately, this course will get into threads and processes, and we have to argue about this stuff. So like you said, like, some questions you might have is like, oh, what order does this run in? Funnily enough, this will actually execute in the same order like 99 times out of 100, but it's like that 1% chance if you actually relied on it running in order that you run into trouble. Yeah. So I'd be running a process that starts executing main first.
Yeah, but the process that you're forking is really replicating essentially.
Whatever is currently running. So the process currently running that fork call. So like, like normally if I ran like hello world or something like that, and we ran this, we would expect this to create a new process and this to start executing at main. So this would be our process. And then in this case, this process would call fork, and it would be a copy of whatever called fork at the time of the fork. So let's go ahead and run this, and we'll do lots of examples. So if I run this, I see both sides of the if branch, but that's not one process executing both sides of the if branch because that's still impossible. We only see both because we execute we have two processes running after the fork. So in this case, I see parent return process ID. So this would be the return value of the fork. So in the parent, I got process ID 31074. So a way to check is we can see the difference between them. So the child got returned 0 from that fork call. And then the child's actual process ID through that get PID system call is 34074, which makes sense because this number, the parent return process ID, and the child should be exactly the same because that's what we defined, that's what the return value of fork should be. So those are the same. We can also check that the child's parent ID, which is whatever created it, is 34073, which is the parent's process ID. So that is what created it. And then you could go further and say, well, what created this process that I just ran on my shell? And the answer to that is, well, this process 22347. And then since we know what proc is, well, we can figure out what it is. So proc status. So that's what created that process. So my shell created that fork example process, and then within fork example, it created a new process, and then that printed out those child lines, and then that process printed out the parent lines, and then they both executed and exited and then stopped. So any questions about that? Yeah.
If I accidentally or intentionally created a while loop of fork processes, would I crash my machine, or is there any way to stop that train before it does that?
Yeah, so what's our question that if we write something like that? Yeah, so if we write this, so this actually has a special name. It's called a fork bomb because it is, so the first time through this loop, it would create a new process, and now there's two processes, and now both of them would go back to the beginning of the loop. Then both of them would create a new process each, so that we have two new processes. And then all four of those will go back and then create two new, and we'll have 8, then we'll have 16, then we'll have 32. So one fun thing you can do to your friends, there's like a shell command that will do this, and it looks really, really weird. And yeah, if you do that, it just creates processes over and over again exponentially, and then eventually your computer will run out of resources and crash. So if you want to provide some protection against it, that's what you have to do as like a kernel. So some newer kernels will actually detect things like this and be like, no, 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 I'm going to kill you before you start replicating. So this is something you can do. But, all right, any other questions? Yeah.
Can you explain what the child return PID means?
So that's the return value of the fork. So here, I'll show it another way too. So we'll go through this like fairly slow. So first, we'll assume we're running this program, and we are running it as a process. And I'll just say, for simplicity, that it's currently running process ID like 100. So if I say I have process ID 100 that something else creates for me and starts executing, I start executing main. So I'll put a blue marker that says where each process is currently executing. So before I'm created, I start calling main. I haven't made any call yet. Then process ID 100 is going to call fork. And now process ID 100 is going to move down here. And as part of that, assuming it's successful, it's going to create a new process. So we would call it, say, process ID 101. And it is also, right after the fork. So right before the fork, they're exact copies of each other. In this case, there's nothing to differentiate them at all. And then the only difference after the fork call is going to be the value of return PID. So in process 100, what would its return value be from that fork? Yeah. 101, because that is the process ID of the newly created one. So it would get 101 back as the return value of fork, and process 101 would get 0 back as that return. So this is after the fork, so it is not a copy because it happens after the fork. The only thing that gets copied are the state right at the fork, not after. So after, they're slightly different, and the only way they're different is that return value. So now at this point, we have two things executing. We have process ID 100 and 101. At this point, you don't know which one's going to execute first. So if you want to if you want to be really complete, you would have to argue about, if this runs first, then I'll see this. If this runs first, then I might see this. And you'd have to do that for every single line because it could get swapped out at any time. And we'll see that a little bit. But now, I assume that if, let's say, for example, it chooses to run process ID 101, well, it's going to execute as we know normally. It would check the if conditions and everything. So in process ID 101 here, whoops. Come on. Yeah, so is in process ID 101, is process ID greater than 0? No, right? So it would fail this, and in this process, it would go to the else, and then check, is the return PID equal to 0? And in this case, it is. So it would go ahead, and the next thing, if it's still executing, would execute this printf, which would execute the child thing. And then eventually, it's going to print off all the statements and then fall out, and then it would just return 0. And in which case, at that point, it exits the process, and that process is no more anymore. And then next, we still have another process executing, so that's process ID 100. So in this case, instead, it would reach the same branch again, so it would reach this if statement, but now it's checking the return PID, which is different between them, and it would actually check that, hey, it's greater than 0 now because it is 101. So it would print off the parent return whatever, and then the other prints, and then because it's in an else if, it would just jump to the end because it's done, it went into the if branch, and then execute return 0, and then it would be done. Yeah.
You said that everything's copies between forks. Does that include static variables? If the two branches, the two forks communicate between each other?
So everything's a copy, and they're all independent. So we can see what that looks like too. Okay, so first here, I'll demonstrate a few other things. So here, whenever I run it, I always see parent first instead of child. Well, the only reason I see that is because I put this command here, which is like a usleep system command or system call, which tells the current process to just go to sleep for a little bit and wait. So it's just kind of wasting time after it prints, which actually shouldn't do anything. And you actually don't know why I put this here. Yeah, this is not here for the reason I thought, sorry. So we'll see why that's there in the next lecture, but it doesn't have to be. But sorry, that was confusing. Yeah, don't worry about that sleep for now. But if I run it over and over again, I always see parent first, although there's nothing stopping child from going first. And I am getting very unlucky. So like I said, yeah. Oh, sorry. You can't see anything. Okay. Whew. Okay, so if I execute this program again and again and again, well, I always see parent first instead of child. And in this case, I'm just getting super unlucky. Okay, I guess this year I just get unlucky. So you can see them in different orders, but it's really, really, really rare, because typically the way the scheduler works is it gives each process like a little slice of time, and in this case it's not really doing anything. So by the time it calls fork, it would probably have some time left to execute, and then immediately continues executing after the fork that original process. So like I said, like 99 times out of 100, you'll see parent first. Yep. Yep, they can be stopped mid if statement as well. So if I wanted to, I could go ahead, if I wanted to like force the issue, I could sleep here. So uSleep will put this process to sleep for 1 second. So in this case, no matter what order, they tend to switch really, really fast. I should see parent return process ID, and then it will be in that block state, and another process can run. So that child process will probably run, print its 3 lines, and then we'll see the parent do the other ones. So if we go ahead and we so if we go ahead and compile that and run it, now we see that, hey, that first parent line happens, then it would switch to another process, do those 3 prints, and then finish the last 2 prints of the child. Yep.
Could it stop in the middle of a printf? Like if you gave it like 100 million letters in a printf?
Yeah, so it could stop in the middle of printf, depending on how printf's implemented, because it may or may not do a system call, or may split up the input if it's like too big. But it would get interrupted at some point. If you have lots of processes running, then they may just, if like there's a line break or something, it may get interrupted in the middle and you see like it split off weird. So yeah, this would happen. Yep.
So when the program first starts, fork is called on like PID 100, right? In the example, like the parent,
Yep.
and not the child. So then why do we get 0 returned for the child then if fork isn't being called on the child?
So the child doesn't exist until fork is done.
So why do we get, like, so in the example, it's like PID 101 as the child.
Yep.
Why do we get 0 returned? Because I thought fork isn't being called on PID 101, but we still get 0 returned from the fork?
So the way it works is only one process is calling the fork in this. So when I initially start here, like when I start running main, I only have my process 100. And then process 100, like 101 doesn't exist yet. So process 100 will call fork, and that will create process 101. And then the only way to differentiate them is the return value of fork. So in process ID 100, it will see 101 returned. And then in the newly created one, it will see 0.
So one call to fork returns 2 numbers.
Yeah, so you can think of that. So after fork, there's going to be 2 processes. So, and the only way to tell them apart is the return value of fork. So there's 2 things that can run, and you don't know what order they're going to run in.
Okay, thank you.
Yep. Yep.
So is this an example of concurrency?
Yeah, so this is an example of concurrency or parallelism. We'll get to that later, but you don't know what it is. Like, you know, we won't have 2 things running simultaneously if I only have a single CPU, for example, but it could run concurrently. Your operating system or kernel is the one that switches between processes that we touched on a little bit. And to see that they're actually like complete copies of each other, well, let's make some variables or do something more interesting. So I have int x equals 42, and I need to switch that. So I have int x equals 42. So if I'm truthful, I would be like, hey, at the fork, let's print so if I do something like that and I run this, what should I see? I should see x equals 42 two times because it's after the fork. If I move it here, what should I see? Yeah, x equals 42 one time because it's before the fork. So let's go ahead and make sure that that is actually true. And so if I go ahead and do that, I see x equals 42, probably from the parent. Yeah, it would be from the parent. Then I see x equals 42 from the child, and they're completely separate. But I mean, I just made the variable. It's not really that compelling. So what would happen if I did something like, so in here, my parent always runs first, or no, my parent always runs last. So let's say in the child, I do something like x equals, I don't know, give me a number, 13. Okay, so in this case, I have x equals 13 in the child and only the child, and here I'll remove that. So anyone has a guess what I'll see printed? Yeah, 1, yeah.
42 from the parent and then 13 from the child.
Yeah, ideally if they're completely independent, well, here before the fork I have x equals 42, and then that exists before the fork, and then I would fork. So both processes would have an x called 42, or the x with the value 42, and then there'd be two independent copies after the fork. So if I change one, it wouldn't change the other. So in here, in my parent, it wouldn't change anything, and then print off x hopefully equals 42. And then only in the child, it would print, x equals 13, and go ahead and print x equals 13. So let's see that. So if I do that, I see x equals 13, and that change happens after I print it. So it definitely happened first. I definitely changed x equals 13 before the other one printed what the value of x is, and I can see it's still 42. Sorry, you had a question?
Yeah, why does it do that? Does the x not refer to the same memory location where the original variable is stored?
So with a fork, they're exact copies of each other, and they copy even the memory contents. So they're exact copies. So this seems a bit weird, right? But this is how it is. Any questions about that, or any other examples you want me to do with that? Yeah.
If you had a file open or something, could you run into issues reading and writing two processes at the same time?
Yeah, so the question is, if I have a file open at the same time and it copies everything, including those open files, well, would I have problems with two things writing to the same file? And yeah, you would, which is, funnily enough, that's why I see both print. So we know that the printfs just write to file descriptor 1, and that's why I see them both on my terminal, because it's a fork, they're exact copies, even their standard outputs. So both processes' standard output go to the same thing, so that's why I see both of them. Okay, so we can see even and by exact copy, I'm going to mean exact copy. So even if so maybe it's okay that they're exact copies in terms of the value of x is the same, but what about its address? So if they're exact copies down to the byte, should they both have the exact same address even though their values are completely the same? All right, hands up, same address. Hands up, different address. Okay, that would make sense that they have different addresses, right? Kind of. Well, if they were exact clones, they should be exact clones. They should even have the same memory address, which seems a bit weird. But if I go ahead and run that, yeah, it complains, whatever. They have the same memory address even. I told you they are exact copies of each other. and they're completely independent. Yeah.
But then we modified it to 13.
Yeah.
So what is this black magic?
It's the operating system. Yep.
Does it happen because of like virtualized memory and this is like not the actual address in the machine?
Yeah. So someone already solved the mystery. This happens because of the magic that we touched on before, virtual memory. So each process has its own virtual addresses, so they're not real physical addresses. So as part of the black magic of your kernel, well, in this process, this address would only be valid for this process to point to a specific location in memory. And in the other process, this address would actually point to a different physical location of memory, even though they look exactly the same. Yep.
So when it's first forked, is it the same physical address they're both pointing to? And then you said it copies on the right, is what you said?
Yeah, so the question is, when the first fork happens, do they point to the same physical memory address? So the answer to that is initially it does, and that makes it fast, but we'll get into the implementation details as to what's actually going on there. Yep.
Maybe this is too in the weeds, but how does it know whether or not something has changed? Like, does it have to keep an entire array for every single byte?
We'll get there. Okay, any other quick questions? Yep.
Is the address of X chosen completely randomly, or if you created X after the fork, would they both still have the same memory address?
Well, we can do that. So the question was, is the address completely randomly, or if I created it after the fork, would they be, completely different? So in this case, if I move the X back one, it's not copied as part of that fork, and then I have two processes that create X as their next thing they do. So if I go ahead and run that, I see that, hey, their memory location are exactly the same. And why is that? Well, X, if I do int X, it's created on the stack. And right before that fork happens, well, that main function has a stack. Its stack pointer is going to be at some address. And at the fork, it's the exact copy. So at the fork, they actually both have the same stack pointer address. So if they both do the same step of just creating one more variable in the stack, they'll have the same address. Yeah.
Do all processes have a set amount of virtual memory, or does it change depending on how much the process is using?
So we'll get to that. Each process has its own virtual memory that's actually mapped to valid addresses.
They can diverge depending on what they do.
Yeah, so here I can make them diverge. They can completely diverge. If I have, if I create a Y here, in this process it would have a Y, and the other one wouldn't. They're completely different now. And in fact, to create a new process, I could do the exec VE here in this one, and it would be a completely new thing. Yeah.
Is there a different useful way of differentiating between processes in a fork? If you want to create a fork but want them to do slightly different things, is this type of if structure based on the return PID the only real way to make them do different things once they fork?
Yep, this is the only way to make them do different things because that's the only return value you get from it. You just get a number and that's it. Yep.
If you malloc X instead of just doing the regular allocation, would it give you a different pointer?
Yeah, so the question is, if I just malloc, do I get the same address? And the answer is, yeah, it would probably set up the malloc library and it would all be the same addresses. So if I do the same step, I get the same thing. All right, well, we'll leave at this for today. We had nothing on in the chat, which was kind of weird, but cool. All right, just remember, pulling for you. We're all in this together. Yeah.